This is the practice for topic 1. As a serious disclaimer, these are not full hypothesis tests. The goal of this is only to practice certain aspects of hypothesis testing. I would assume that most people would need more practice for setting up HO and H1. And in the topic 1 folder, there is a full practice. I think there's about 24 problems on there for given a claim, state your HO and your H1. So I'm going to do the first 3 with you on this video and then leave the solutions for the last 3. And as always, if you have any questions, please send me an email. So for each of the questions, we're going to state the claim, the null and the alternative hypotheses, and then draw a picture for whatever our parameter is. We're also going to label the null hypothesis on the picture and state whether the test will be left-tailed, right-tailed, or two-tailed. And this is actually all of the steps, all of the parts for step 1 in hypothesis testing. But if you watch the other video, I did mention that step 1 is definitely the lengthiest step for hypothesis testing. So the first question, in an example, example 1, in a research poll of 745 randomly selected adults, 589 said that it is morally wrong not to report all income on tax returns. Use a 0.01 significance level to test the claim that 75% of adults say that it is morally wrong not to report all income on tax returns. So this is an example of a question you would get in another topic, but normally you would have to do the entire hypothesis test. So again, in this practice, we are only doing step 1. So step 1 is state the claim, HO and your H1, your hypotheses. Draw your picture, label your HO on your picture, and then state whether you're left-tailed, right-tailed, or two-tailed. So there's a lot going on in step 1, but fortunately, this is the huge major structure of every single hypothesis test. So first, the claim is the proportion is equal to 0.75. That's what we're saying here. Test the claim that 75% of adults. So we are testing a claim about a proportion. So sometimes you can do a mean of proportions, but this question doesn't indicate that at all. So we have the proportion is 0.75. So we're basically taking the language of the problem and rewriting it in mathematical statements. Now, what you want to remember is that HO only has an equal sign, okay? So it can only have an equal sign. So whenever you have equality in your claim, it's automatically going to just be HO as it is if it has just an equal sign already. So HO can always and only have an equal sign. H1 needs to be, so these two cannot be true at the same time. So if HO is that it's equal to, your H1 is going to be not equal to 0.75. They're not always going to be opposites though, but for now these two are opposites. So this is a nice one to start with. Now, your next question is, okay, I'm dealing with proportions. What picture do proportions have? Proportions follow a normal distribution. So this means that if I had this population and I found this proportion over and over and over again, it would follow a normal distribution, is where that comes from. So HO we're assuming to be true. So this is basically like, normally we put the mean here. Well, it's the same thing for proportions. We put that right smack dab in the center because we're assuming that that is true. Lastly is deciding whether we have left tail, right tail, or two-tailed. On the answers to this one, there's a written version of these answers. The tails are shaded, but I actually recommend waiting to shade the tails until you actually know how big they are. So this is going to be two-tailed because we have a not equal to. That's it. You look at your H1 and you decide whether you have left tail, right tail, or two-tailed. When we do a specific example, I will explain why this is the case, but for now, we're just going to roll with it. So this is two-tailed since H1 has a not equal to. So originally it seemed like a lot of steps, but they all flow together. And this is what we will find for steps 1 through 6 of hypothesis testing. Once you get to step 3, I say the dominoes fall, and then the rest of the problem is you're just done super quick once you've set all of this up. Step 7 is kind of a standalone, but we will get to those. Step 7 is actually basically a Unit 3 problem. So at least it's something that we've already done. So setting up the claim, hypotheses, picture with your HO labeled, and whether you have a left tail, a right tail, or two-tailed, that's the process for these problems. So the second example, a random sample of 40 salaries of NCAA football coaches has a mean of $415,953. The standard deviation of all of these coaches is 463,364. First of all, this should seem weird to you. The standard deviation being larger than the mean means that there is a very, very big amount of deviation. So the values really fall from the mean pretty widely spread out. Use a 0.05 significance level to test the claim that the mean salary of a football coach in the NCAA salary is less than 500,000. Well, some people might say, well, yeah, the mean is less than 415,000, or less than 500,000. It's 415,953. But this is just a sample. We need to take into account how many we've done as well as how much they vary. So this is why we need to run a hypothesis test on a question like this, because we didn't do a census. So if you want to do a census and sample every NCAA coach, that might be something you could do. But if you're looking at everybody in the United States, that's a whole different shebang. So I would pause and set up the, the claim HOH1, your picture, and your tails. But the claim here is that the mean is less than 500,000. So the mean we're referring to is the population mean. It's the mean of every single coach ever, because we already know what the sample mean is. We don't need to test anything on that. So the mean is less than 500,000. HO, however, is always and only going to have an equal sign. So your HO is going to be mu is equal to 500,000. H1 is going to be your claim directly. So these two are not covering 100% of the number line, because this is a moment that the number equals 500,000, and this is every moment less than 500,000, but this is okay. They just cannot be true at the same time. So now, this is actually going to be a t-distribution because we don't know the population standard deviation. That's not given to you here. But we're drawing the same shape for the t-distribution, basically. We also know from the central limit theorem that once you get above 30, you're going to basically follow the z-distribution anyway. So drawing the same bell shape isn't weird. HO, we're assuming to be true, goes smack dab in the center. This is going to be a left-tailed test because our H1 has a less than. That's it. So this is really going to be the challenging part, is setting this up and assuring that you are accurate. And then from there, they do start to kind of fall into place. So the example 3 gives us the one really weird scenario that we will run into, but luckily we boil it down to a specific, situation. So the heights of 33 popular supermodels is measured, and it's found that they have a mean height of 70 inches and a standard deviation of 1.5 inches. Use a 0.01 significance level to test the claim that supermodels have a height with a mean that is at least 67 inches. So at least is that language again where we have a greater than or equal to. So our claim is that the mean is greater than or equal to 67. This is going to be HO, but in disguise, okay? Because HO always has to have an equal sign. We have equality here. So since there is equality, this is going to go into HO directly. Okay, so it's greater than or equal to in disguise. Now, what this means about H1 is that it has to be a less than so that these two do not overlap in any way. So again, our claim had equality in it. It had a greater than or equal to. As soon as you say equal to, this means that this is going to be your HO with an equal sign because it has equality to 67. Then H1 needs to be less than because HO is a greater than or equal to in disguise. So whenever your claim has equality, if it's just an equal sign, it's okay. But if it has a greater than or equal to or less than or equal to, it's probably going to be a slight pain. But if you do the extra practice for this, you'll get a chance to practice a large number of these. So I recommend doing the extra practice. I spend 2 days on topic 1 in class, so you really should be treating this as basically a double topic. We're again going to follow the normal distribution, or actually the t-distribution, but our sample size is more than 30, so it's going to be almost the same as the z-distribution anyway. HO goes right smack dab in the center, and we are going to be, again, left-tailed. So examples 4, 5, and 6 look at 2 population examples. They are going to have a slight difference, but I actually think they have a slightly nicer edge to them. In general, I don't expect you to be 100% proficient in step 1 of hypothesis testing. When we do topic 2, it is at that time that you'll start to put all the pieces together and you'll start to be able to do it on your own. But for now, take the time to practice step 1. It's definitely going to pay off in the long run because we're going to be doing hypothesis testing for the rest of the semester, and being able to set up the problems is going to be absolutely key in your success with these topics. As always, please feel free to email me if you have any questions.